In this video, we look at how we find definite integrals. So to find the net area under a curve, it means the area of the curve between the curve and the x-axis. So if you're above the x-axis, these green regions, these are positive areas. When you're below the x-axis, we would consider these negative. So the net area is the total sum of all those parts, so positives plus the negatives. Now when we worked with our Riemann sums, we took each rectangle and we found the area and we added those together. But we said the more rectangles we have, the more precise our area would be. So to find the most precise area, we're going to keep dividing this up as n is the number of subintervals. So here I had 6 subintervals, here I have 40. I'm going to keep increasing it until n reaches infinity. And I'm going to take that limit as n is approaching infinity of the summation of the areas. So this f x star k delta x is just our area formula in disguise. So delta x, that's the width of each rectangle. Xk star is where we're finding the height of the rectangle. So if I want to find my height right here, I would start at my first bound, which is a, and I have to add that x1 star. So then when I plug it into f, that's giving me my height. So the whole thing f of xk star is the height of the rectangle. Right? And we're just finding areas, so width times height is the area, and then I'm adding up all the areas. So our formal definition for the definite integral is that a function f that is defined on the closed interval ab is integrable on that closed region AB if the limit, as the change goes to 0, that width of my rectangles, is the summation of the areas exists and is unique over all the partitions, meaning all of those rectangles, and all choices of xk star in the partition. So this is the definite integral of f from a to b. So this left-hand side is the definite integral, the integral from a to b of f of x dx. Right, so the integral from a to b of f of x dx, and that's equal to the limit as delta goes to 0 of the summation of the areas of all of our triangles. Okay, so to break that down a little bit more, there's lots of notation here. So this is my integral sign, b is my upper limit of integration, a is the lower limit of integration, f of x, the thing we're taking the integral of, is called the integrand. Over here, when I'm working with the limit function, I have the lower limit of summation, the upper limit of summation, my height, and my width, where x in all of these is the variable of integration. Now remember, to figure out the width of our rectangles, we take the difference in the interval, the closed interval a to b, so b minus a, and we divide it by n, where n is the number of rectangles that we want. So that's how I get my width. To figure out where I'm using xk, I have to say, well, wherever the interval started, and I have to add on however many widths I have. Remember, we use left bound when we're doing these. So this a is going to be the starting one. So if I haven't gone any rectangles over any widths, it would just be a for my first rectangle. And then I keep adding on that difference to figure out what x value I'm at. But then I have to plug it into the function to evaluate the height at that specific x value. Okay, so we need to make sure we can rewrite our limits as definite integrals and vice versa. So here we have 4 minus xk star squared on the interval from -2 to 2. So if I want to rewrite it as the definite integral, I'm going to use my integral sign. My lower bound is -2, my upper bound is 2. The function is 4 minus x squared in parentheses, and we're doing it with respect to x. So this is now rewritten as my definite integral. Okay, so we need to evaluate these. Well, there's two ways to evaluate our definite integrals. So the Riemann sum is a close approximation, but it's not going to be a precise exact value. So one thing we can do is, if I can graph it and see very easily what the shape is, and I can take a finite area, I can use the area and just do it geometrically. Otherwise, we're going to go with limits. So let's start with one that works for geometry. So I have the integral from 0 to 2 of 1 minus the absolute value of x dx. And we want to sketch by starting f of x equals 1 minus the square root of x. So here are my x and y axes. This is an upside down absolute value that's been shifted up 1. So it shifts up 1. At 1 it will be at 0. At 2 it will be at negative 1. At negative 1 it will be a 0. At negative 2 it will be at negative 1. So here's my graph. And we are looking specifically for the area from 0 to 2, the area under the curve. So that's this piece, and that's this piece. Well, I can see that these areas are rectangles, so my upper rectangle, my area is 1/2, my base, which is 1, times my height, which is 1. And then the second one, which is below, I'm going to say minus, it's also 1/2 times 1 times 1. So this area works out to be 0. The total net area is 0 because the region above the x-axis and the region below the x-axis are the same side, so they're adding up to 0. So the net area here is 0. Now I could also ask for total area, and that is a little bit different. Total area is not net area. Total area is all of the regions. So here I wouldn't care if they were positive or negative. I would have to take the absolute value of each, in which case my area here would be a 1. So this one I can use geometry. I had a nice shape, nice rectangle. Nice triangle. But a lot of times, especially when we're working with calculus, we're not that lucky. It's not a nice shape that we can recognize and take a nice area of. So this is where we're going to use our limit. So we rewrite the formula just a little bit. Instead of using as delta approaches 0, we're going to switch and say as n approaches infinity. So that means the number of our rectangles is just increasing to infinity, and we're squeezing in as many possible rectangles as possible. So notice as delta goes to 0, right, the delta xk, as that's approaching 0, it means that n is getting bigger and bigger and bigger. So that's why this is a legal change. And everything else here is staying the same. K is still starting at 1 and going up to n. We still have our height, f of x star k, and our width, delta xk. Again, to be able to evaluate these so we know when we're plugging them into our formula, to get our width, we take the difference in the interval, divide it by n, which is the number of rectangles, so it will be left in terms of n. Then we have to get x star k to know where is that left endpoint for each of these rectangles. So we start at the left endpoint A, and then we're adding each interval on to find out where that next value is, and then we plug that in to find the height of the actual rectangle. Evaluate this. Okay, so and we're doing this using limits. So we want the limit as n approaches infinity of the summation from k equals 1 to n of f of x k star delta xk. Okay, so we need to figure out what all of these things are. So our delta xk is given by the change in our interval, 5 minus 1 over n, so this is going to be 4 over n. Our x star k is equal to the first value a plus k times xk, 4 over n. So this just tells me that for whichever k I'm at, so if I'm at the third rectangle, I'm going to add that width 3 times to where I started. Okay, so then before I can plug it in, I need to figure out what's f of xk star. And f of x is 1 minus x, so I have to do 1 minus 1 plus, and I'm just multiplying and cleaning this up a little bit, 4k over n. So my f of xk star is just equal to negative 4k over n. Okay, so now we have all of our pieces. I'm going to plug them into my limit function. So I have the limit as n approaches infinity of the summation from k equals 1 to n of negative 4k over n times 4 over n. So multiplying that out, I have the limit as n approaches infinity of my summation of k equals 1 to n of negative 16k over n squared. And so from when we were working with our Riemann sums, we also looked at how we evaluate summations. I know that the constant part is the negative 16 over n squared. That's not being changed because k is the variable on this piece. So I'm still taking the limit as n approaches infinity, but I'm going to pull that constant out front, negative 16 over n squared, times the summation from k equals 1 to n of k. And this is a formula. So I have the limit as n approaches infinity of negative 16 over n squared times n plus 1 over 2. So I have the limit as n approaches infinity. And as I clean this up, this is going to be negative 16n squared minus 16n all over 2n squared. And now we're just taking our limit. We know as n goes to infinity, because the exponents are the same in the numerator and denominator, I can use my rule that says if the exponents are the same, the limit is equal to the coefficient of our values. So this is just equal to negative 8. Now, if we were to take a second and actually sketch this graph, kind of running out of room, so I'm going to squeeze my graph in up here. The graph of 1 minus x is just a straight line. It has a slope of negative 1, a y-intercept of 1, so it's going this way. And we're only looking at our graph from 1 to 5, so we are looking at this region here, which is technically a rectangle, so our geometry would work. This difference is 4, this goes down to 4, and because it's below the x-axis is why our area is that negative 8. So here we want to evaluate the integral from negative 2 to 1 of 2x dx. So we need to figure out what is our delta xk. So that's our right bound minus our left bound over n. So that's 3 over n. Our xk star value is equal to our left bound plus k times our width, 3 over n. And then we need our f of xk star, which is 2 times that negative 2 plus 3k over n. So now we are ready to actually work with our limit. So we know that this is equal to the limit as n approaches infinity of the summation from k equals 1 to n of our f of x star. So when I distribute this, I have negative 4 plus 6k over n times our width, 3 over n. So cleaning this up a little bit, we have the limit as n approaches infinity of the summation from k equals 1 to n of negative 12 over n plus 18k over n squared. Now when I'm taking my summations, I can take the summation of each individual piece. So this becomes the limit as n approaches infinity of the summation from k equals 1 to n of negative 12 over n plus the summation from k equals 1 to n of 18k over n squared. So now I'm taking the limit as n approaches infinity. Now the summation for k equals 1 to n of negative 12 over n, negative 12 over n is a constant, so that's actually getting pulled out front. And so I'm just taking the summation of 1, so when I multiply 1 by itself n times, I get n. Plus, over here, the 18 over n squared is the constant. So then I'm taking the sum of all my k terms, which is n times n plus 1, divided by 2. So cleaning this up, I have the limit as n approaches infinity of negative 12 plus 18n squared plus 18n all over 2n squared. And when I take my limit, I take the limit of each individual piece. So the limit as n approaches infinity of negative 12 plus the limit as n approaches infinity of 18n squared plus 18n over 2n squared. So the limit as n approaches infinity of negative 12 is just negative 12. The limit as n approaches infinity of 18n squared plus 18n divided by 2n squared, because they're the same powers, numerator and denominator, it's just the coefficient, so that would be plus 9. And this turns out to be negative 3. Here we have a table of some properties of definite integrals. I found this one online, but we also have some in our book. You can use lots of them. For all of these, our functions have to be differentiable functions. So if I have a function f of x, and I'm multiplying it by a constant out front. So I have a k here. I can move that constant in front of the integral and then just take the integral of the function. I can negate a function if I'm integrating from a to b and I want to reverse that order and go from b to a. It just means I negate that integral. I can decompose a function for its integral. If I'm going from a to b, I can break it down to a to c and then c to b, as long as c is between a and b. If I'm taking the integral of the addition of two different functions, I can break it apart and find the sum of both those integrations individually. And the other one is a zero integral. If I'm integrating from a to a, I'm not going anywhere, it always has to be 0. Okay, so here we're just practicing with those properties of integrals. We're given two integrals to start. The integral from 2 to 6 of f of x dx is 10. The integral from 2 to 6 of g of x dx is negative 2. So for the first one, if I want to find the integral from 2 to 6 of f of x plus g of x, that's the same as saying the integral from 2 to 6 of f of x dx plus the integral from 2 to 6 of g of x dx. So then we know that this is 10 plus negative 2, so this is just equal to 8. For the second one, we have the integral from 6 to 2 gx dx. So if I want to switch those around and make it 2 to 6, I have to negate it. So this is the negative integral from 2 to 6 of g of x dx. So this is just negative times negative 2, which is positive 2. And this last one, the integral from 2 to 6 of 4 times f of x dx. Because 4 is a constant, I can pull the 4 out front and say it's 4 times the integral from 2 to 6 of f of x dx. So this is 4 times 10, which is just equal to 40.